This video is in response to people asking me how we can size the mechanical systems for the projects that they are designing this semester. To help with that, I'm just going to dive into it. There's a lot to it in a way, at least a lot of variables. So ask me questions. I'm going to go through this quickly so that this is not too long. I prepared a spreadsheet modeler that's available in the resources section of Canvas, and we're going to be using, so that's this, and we're going to be using the Climate Studio thermal analysis results as the data to size our system. Okay, so the first question is, when can we size? At what point in the project? My answer is that as soon as you have a massing and you have a program that's the massing is based on, then you can start sizing. Now, of course, if you've been doing this for a long time and you're designing the same kind of buildings, you'll know the sizing somewhat before you start. But at this point in our careers, it's really good to have the tools we have available to us, and we should use them for this very basic and approximate sizing. So I'm using the project that we did last semester, Environmental Systems 2, as a warm-up at the beginning. The program is a pickleball court with an indoor bleachers, so I can look up the size of that. I know I need a mechanical room and lockers. I'm going to have some kind of small lobby and an office, so I just rough it out as a massing and create a single zone. And then I pick templates and settings that I think are relevant to my program. So I've got, for example, I'm using 90.1 envelope. I've got basic. I understand something about the air tightness, and I'm using a window-to-wall ratio of 0.4 because that's the code maximum. I am choosing glazing that meets 90.1 specifications. So this is all done with very little information other than the program and what I know about performance. Then so I can run a simulation. Oh, and one other thing is that my mechanical system is what's called the ideal air load. We've talked about this. It is a system in Climate Studio that is ideal because it's delivering the exact amount of heating and cooling to the zone as you've defined it, not worrying about ducting or other complications. And so it's a very rough approximation, but it allows us then to have a mechanical system so we can get an estimated energy use, but and it will be constant, so that the system's constant, so that as we're changing other parts of the project, like siding and envelope configuration, we can see the relative effect of those changes. Okay, so then I ran a simulation, and I've got the typical outputs we're used to, energy flows that I can continue to optimize if I want to, looking at windows or infiltration or whatever. But how can I, from this data, get a sizing for our mechanical system? Let's remind ourselves the mechanical system is, to put it simply, divided into three components: something that's delivering heating and cooling, a distribution system for that heating and cooling, and fresh air. We need fresh air delivered to each occupied zone. So what determines the size of the heat? Let's design the heating, or let's size the heating and cooling system or equipment first. The size of that equipment is determined by the peak heating and cooling loads. And that just simply means the coldest day of the year, when we're losing the most heat through the envelope and we're bringing in fresh air and losing more heat from that, even though we have injury recovery ventilation. It's the worst case situation. What size of equipment do we need to replace that heat we're losing, or that the heat that we're gaining from in a cooling season? What size of equipment do we need to deliver that peak? We can get that from the Climate Studio simulation data, thermal simulation data. We have peak heating and cooling weeks. And by the way, I've got a version of the modeler that I've already filled out so that we can move through this more quickly. Uh, I can see that according to my simulation, I have a peak load in July of 14 tons. Why tons? That's ice. We used to cool buildings with ice, and so this is a holdover. 1 ton is 12,000 BTUs. So I'm going to put my peak cooling load of 14 tons there. I've got a peak heating load of, let's see, 215. I'm going to put that as my peak load for heating. And with that information, we can now get a very rough estimate of the size of the equipment. Now, that's based on the idea that we are delivering everything from a centralized source. So one piece of heating equipment and cooling equipment are delivering temperature to the entire building. If we want to go do a more complicated system, we can do that. But let's just start with this. And all I do is just go look up. Let me find something that will deliver 14 tons of cooling. By the way, this is a good time to use AI. I would like I'm using the chatbot in Microsoft Edge Copilot. It's just a good way of, rather than just typing in 15-ton air-cooled chiller in a browser, if I make a query to a chatbot, then I can get a list of more of these more quickly. I can ask for a summary chart. It's a good thing to, good way to start practicing this, because there's some really good things that AI can do for us. But the point is that I can find a piece of equipment that delivers my peak cooling load, and I can get a size for it. Right, so now I know, okay, I've got something that has a piece of equipment that's going to have to sit outside on the roof or on the side of the building. I have an approximate size, so I can start thinking about it as part of my design from the very beginning. I can do the same thing with the heating load, 250,000 BTU condensing boiler. I've got a size. I just noticed that this is shipping, so it probably has packaging too. I don't know, but the point is, we can get a size. We can look at the specs. And why not be looking at real equipment as soon as possible? Because we can get drawings of it. We can get other information from the manufacturer that we may need, and it's something that we can actually purchase. So it's a good process to start, or good practice to start getting into. Okay, so we have at a very basic level, with a really simplistic summary of our energy needs that generate a system size. We have a heating and cooling equipment size. Okay, so what else do we need to do to size the system? We need to distribute that heating and cooling. So let's say in this case we're deciding that we're going to move the heating and cooling through air. And of course we also have to have ventilation air. So we have to design a duct that can deliver our peak heating or cooling load, whichever is the largest, and our ventilation air in the same duct, right? So what's the process for figuring that out? Let's just think about it. If we know the peak amount of energy we need to move, so the question is, how much air do we need to move that heating or cooling load? And that's going to be in CFM. And then from a certain CFM, we can size our duct. So in other words, we need to size a duct large enough to be able to handle that amount of air. So how do we know what the CFM requirement is? Well, basically, it's just a function of how much the set point for the zone. So in this case, I'm going to set my cooling set point at 75 degrees. I think that's a fairly common, especially in commercial buildings, a cooling set point. Then I need to know what my supply air temperature is, and so I've got these terms clearly identified over here. So hopefully this will be a helpful chart. Okay, so I have a supply air temperature for cooling at 55 degrees. I would use that because that's a good rule of thumb. And my set point is 25 degrees. So I've got the delta T between the air that I'm delivering and my set point is 20 degrees. And if you think about it, so then we're saying we have a peak amount of how much air do we need to move? I guess I will mention this formula, but it may just confuse you. One way I use this kind of thing is I get all I just write in all um, the units, and then I see how they cancel out, and that helps me understand what's going on. But basically, what we have here is we're saying we're delivering a certain amount of a peak cooling or heating load. That's the Q, and the amount of air we need to deliver is going to be the relative to the difference in temperature between what the air we're sending and the temperature we want in the room. The only other thing we need to know is we need to have a constant that allows us to convert and to consider how much air, the density of air, the specific heat of air. There's a certain amount of heat that air can move, and so we have to include that in our equation. Okay. Anyway, the point is we're moving air that has a delta T of 20 degrees. And that's generating a CFM of 7,778 cubic feet per minute. Okay, so is that what we're going to use to size the duct? Well, we don't know because what about our heating load? Is that going to be more or less? So we do the same thing here. For heating, we're going to have a set point of 95 degrees. That might change based on your system that you're using. That's a good rule of thumb. That's the supply air temperature. Our heating set point is 68 degrees. That's another typical one. But again, let's say we were designing an old folks home. We might have to make that 75 or 80 or something. I don't know. So that's a variable. But the point is, in this case, the difference between our supply air for heating and our set point is 27 degrees. So we're going to be moving a lot more heat in that air or temperature in that air for heating than we are for cooling. So that is actually going to, that means that we're going to need less air to move that amount of heat. Okay, so that means that we're more efficiently, we're using less air in the heating side than the cooling side. But, no but. So we have a higher peak load, but we have a lower CFM. Why is the peak load for heating, though, higher than it is for cooling, right? The reason there is because we have something called design temperatures that come from our climate. Let's just talk about that for a second. If I go to the climate tab in Climate Studio, this is part of the climate data. We're in ASHRAE climate zone mixed 4, that's 4A. And in that zone, we have design temperatures for heating and cooling of 16 degrees and 91 degrees. And so that's what I put here. What does that mean? And you notice there's a percentage here. So it's basically we're saying that almost all the time when we're needing to cool, our temperature is going to be below 91 degrees. Almost all the time when we're heating, our temperature is going to be above 16 degrees. So we're going to design our system based on those values. Now, there are a few hours of the year that are outside of that range. And in that case, we're going to use a secondary system. Like so for heating, it might be electric resistance heating underneath the desks in people's offices. For cooling, it might be a ceiling fan. Okay, so that's where we get these design temperatures, and they're coming from the climate. If we look at the difference between our set point for cooling, 75 degrees, and our cooling design temperature, 91 degrees, we get what is that, 75, 85, that's like a 16-degree differential. So between the peak amount of temperature outside, the peak temperature outside, and our set point. For heating, our set point is 68 degrees, and our design temperature is 16 degrees, a much larger differential. So that's why we have a higher heating load than cooling load. But since we're delivering air with a lower temperature differential between the supply air, cooling air, and its set point, we actually have more CFM that we need to deliver this smaller amount of load for cooling than we do for heating. So now that's going to be a lot of information. Maybe it's confusing, but I'm just trying to give you the reason why all these values are here, and that we're going to now pick the larger CFM from cooling, the 7,778 CFM, to size our duct. However, we also need ventilation, right? So we need more information before we can know how big the duct needs to be. Information do we need, and where do we get it from? Oh, and by the way, let's look at, so these settings here, we already said that these two are they're already in our model in the climate section. These other settings are here too. So we have in our space use template, we have our set points, 68 and 75. So those were already set. And then we have other variables that are identified that have to do with ventilation. So let's go over those in order. So the first thing we need to know is the area. Okay, so how do we calculate how much CFM of ventilation air we need? We need to know, there's two variables. Actually, I will go back to this. I think this is the right time to do it. We need to deliver a certain amount of ventilation per person. And this 7.5 that I've got here comes from this chart that I gave you. And this is based on New York City Energy Code, which is based on 90.1, ASHRAE 9.1. I think so let's just say that we're going to, if we're talking about meeting New York City Energy Code, we would set as a minimum our CFM at 7.5, or let's just say at 7.5. So that's per person. And then we also usually have a ventilation amount for the space itself. So just, we have pollutants coming off of, we're off-gassing from materials. We have other pollutants in the air that we need to get out. So we have both a fresh air per square foot of area of the space, and we have a CFM per person. So the 7.5 and the 0.06 I put in CFM per person and CFM per square foot. But to get actual CFM from that, then so to get the CFM from the CFM per people, we need to know how many people we have. How do we do that? Well, first we need the area of the space. And so if I come to my thermal zone here, I've got that information right here, 4672. It's also in the results. If I come down to the bottom of results, I have the square footage. Okay, so I've got the 4672 square feet. I also need to know how many people I have in the space, right? So where do I get that from? If I come back to my space use, space use loads, I have a people load here. In Climate Studio, they do it it's people density, people per square foot. In our code in the U.S. and the IBC, we do it. This is from the egress occupancy. It's in square foot per person. So if we just take the we divide the 1 by 0.02, we get 50. That's 50 square feet per person. If you look up in the egress occupancy, that's typical for assembly. So this makes sense. Okay, so we have 0.02 people per square foot. We know how many square feet we have. We multiply those together. We get we multiply the area times the number of people times the CFM per person, and we get a value. If we multiply the CFM per square foot times area, we get a value. If we add those two together, that's this. We get a total, and that's 946 in this case. Okay, so now we have a peak CFM that we're saying from cooling of 7,778, and a peak, we have a ventilation requirement of 946. In this cell, I've added those together. I've got this thing where I'm taking the max from these two cells and adding it to the total ventilation. So you don't have to do anything to make that happen, but I mean, it's automated, but just realize that's where it's coming from. And so now I have a CFM total of 8,724 CFM. So how do I get a duct sizing from that? There's a bunch of places you can do it, but I've just given you this link to a duct sizing calculator. I'm going to put, I already did, I put in the 8724. The only other thing you need to do here is pick another variable. So I would pick friction loss and put it at 0.1. You don't need to know what that actually it's. You don't need to know the units, but just think of it. That if you have a duct, you're going to have friction because you have air pushing, running by it, and the type of the material of the duct and its square footage in relation to volume is going to determine a certain amount of friction. So we define that, and then we get an output from that of a duct sizing. Now, if the way I've got this set up here is I'm just going to square these. So I've got a rectangular duct of 28 0.76 square inches. I'm going to square it, and then if I divide that by 144, I get 5.7 square feet, and that's what I put here. So I need to find a duct that has 5.7 square feet. If I say, no, you know what, I want to actually limit that. I want to say I want my duct to only be 18 inches deep because I have a certain amount of room that I'm thinking about in my plenum or whatever. Then I can get an output of the so it's 18 inches deep, and I'm going to have a 46-inch wide duct. So that's how I can use this information. The other, so that's our trunk. Now remember, the trunk is coming off of our air handler, and it's all of the air for the zones coming out of, or for several zones, or however we get this set up, is coming down the trunk, and then I'm going to branch off of that into individual registers or different zones. And so there's a rule of thumb by which we take the trunk duct and we multiply it times 1.2 to get the total, the sum of all the branch ducts. So think about it, that you've got amount of air moving in a trunk. You're going to branch off of that to deliver it to the individual rooms. It's going to be the same amount of air because we're just branching it off, but you're going to actually need more duct. You're going to need more duct surface area because these branch ducts are smaller, and that means that their surface area to volume ratio is going to be larger. You're going to have more surface area, and that's where the friction happens. So we actually just have a larger aggregate of branch duct square footage than we do of trunk duct. That's automated. That's created. That calculation is done automatically in the spreadsheet modeler I've got here. Okay, so we have an estimate for our heating and cooling size. We've got an estimate for our trunk and branch ducts. So at this level, we have now completed the design of our mechanical, or the very rough estimate of sizing for our mechanical system. Let's go one step further. Let's say that, so I'm back at my gym, and now I've gone further in my design, and I've divided this into 3 zones. And the numbers are going to be different here because I've done other things here. I've optimized. So I've got a 90.1 version of this and an optimized version of this. And so the actual numbers don't really matter so much, or I'm not worried about that. But I want to explain to you a way that you can do a more complicated, or you can go into a more nuanced design of your mechanical system. And this is where we're using actual mechanical systems that are available in Climate Studio, and we're going to separate our zones in case we want to have different systems for different zones. Okay, so how would I do that? So I've run a baseline. This I started with a really bad envelope that like a 1960s all concrete, no insulation, single pane glass, not that great of a mechanical system. I typically do that to kind of start with something and improve on it. And then I went through 90.1 optimizations, and then I used what I know about how I could improve the envelope to a pass-fault level and pass-fault infiltration. My point is that I've already optimized this to some degree. And then the envelope and the passive portions of the system. Then I ran a simulation with all 3 zones using a VAV system and a boiler. And remember, that's so then I would set up. And by the way, so I can have I can bring as many of these different systems down as I want to. So I have two different VAV systems because I end up I'm going to have a VAV in my gym and a VAV in the mechanical system, and I'm going to end up with a VRF in the lobby office zone. Um, but for now, I chose a single. I assigned zones all to one VAV system, and I had it set for whatever I had it set for. In this case, it's a condensing boiler. I think at that point I just had a regular boiler. We've gone through this how you would set these up. My point is just reminding us that's what's been done. You're not going to understand my code here, but I understand it. You should try to organize this in a way that let's say I open up this model in 6 months. If I don't have these clearly labeled, it's really not going to be useful to me. I open up models year after year, right? So I try to make these clear enough so that they're useful tools for me, and I would suggest you take that time to try to start getting into that habit. Okay, and so then what I did next is I tried different mechanical systems for. So I have the VAV boiler system for both the gym and the mechanical lockers room, and then I have a VRF for the office lobby, and then finally I changed my heating and cooling delivery for the VA system to a air source heat pump, and I kept the VAV for the office. So I'm saying I went through a process and tried different mechanical systems. And so then let's say that I'm going to go to the optimize. I'm using this now, this configuration. But if you look at it, there's two things to notice here. Well, actually, not two things. Right now, I'm just going to, if I, if I look at my peak heating load, it's like I was doing before. I've got a peak load that's much lower because I've optimized. And by the way, I think that these loads are maybe ridiculously low. I'm not saying that we're being completely accurate here. This is a process. The point is, though, that my peak load right now is for the entire all three zones, right? It's not. And so if I'm trying to have different systems for the different zones, I need to have a way that I can isolate the zone. And so there's two ways that you can do that. One, you could just run. You can turn off the mechanical systems in the other zones. And so, like if I were to say I just want to run the gym with the settings I had, I could set this up like that and run it. And then what would I have? I would have a gym with a mechanical system, and then two unconditioned spaces next to it. What that does is I can get and I'm not saying again, I don't know what would be the best way of doing it. I would have to talk to a mechanical engineer, and we would go over, the way I'm doing this and the systems I'm using. I mean, try to understand how Climate Studio is getting these values. We're just learning a process. But if I look at so I've got a peak load here, just running the gym in the way I just said, of about 24 kilobtus. If I go, there's another piece of information here that we've not talked about, and that's the zone temperature curve. We see that when I have these two zones without mechanical systems, that I've got a very wide variety. I mean, because they don't have mechanical systems, so I've got a lot of. Okay, let me explain this. The gray here is the comfort zone. And so what it's saying is those two zones that I don't have mechanical systems on are obviously their temperatures are well outside of the comfort zone. So that means that some of the heat from the gym is leaking into the mechanical locker room. It's probably not the most accurate way of doing it. Actually, I'm gonna switch to another one that's a little clearer. If I go to, I did this work for the office. So I've got that situation where I've got a pretty wide variety. If I then say, okay, I'm gonna use a different method. I'm going to actually turn off my other zones. So I'm going to turn off the locker and the gym. And let me just turn off the text because it's maybe confusing. And then I'm going to add an adiabatic surface for the lobby. So if I go, remember I can add an adiabatic. So basically what I'm saying is I'm just isolating this one zone. I'm isolating this one zone now. I basically, I've like waxed off the wall, and I've still got it's still connected to the building. It's part of the project, but it's by itself. And the difference here. So let's look at the two. So my peak load. Um, so let's do my peak heating load is about 15.5 for the little office lobby area. Um, and if that's with when I did it connected to the other zones. If I do it with this adiabatic surface, it's a little bit lower. So now I'm at like 13. But what happens if I look at that? Which one's more accurate? Well, if I look at my comfort curve, when I'm running a single zone, um, I'm completely within my comfort range. And again, if I go back to the other approach I did, where I've got these unconditioned zones outside of it, I've got some leakage. I'm not exactly sure what effect this is having, but I'm thinking it's like less accurate. So in my mind, I'm going to use this approach. But again, the point being, I am to some degree playing around here. I'm getting something that's much better than nothing, and I'm learning a lot. Okay, so that's the way in which then I generated these individual uh, peak heating and cooling loads for my three different zones. And so a completed modeler here would look something like this. I've got, I have to have my variables um, from the climate that we talked about. I named the zone. I described the mechanical system so that I have some context here, and then I put in the same values that I did before. Um, so then I'm going to size the ducting for individual zones. So what's going on there? I've got uh, for the first two zones where I'm using VAVs, I'm doing the same thing. I'm just sizing them based on the totals. But the third zone, why do I have this tiny amount and I don't have anything? Actually, I shouldn't have put this here even. I don't have anything for heating and cooling. Um, Though actually, that's wrong. I should have the heating and cooling totals. So because I want to know the size of the system. Let's see, what would that be? That's this one. What did I have? Peak heating of 13. Is that right? Yeah. Okay, so what's the point here? Is that I am not moving heating and cooling in this zone through air. I'm moving it, since it's a VRF system, I'm moving it through refrigerant. So the only air that I need is for ventilation. That's a really small amount, 62 CFM. I've got a 5-inch in diameter duct. So let me look at that. If I put into my modeler 62 CFM, I've got a 5-inch. I'm probably going to use a round duct. They're flexible. I can move them even through walls or through small chases. So it's a different metric here I'm using. I'm not using square foot. I'm using just the diameter, and that's what if I were looking at a round duct, I would be looking at the diameter. So in this case, I am sizing just the ventilation system. I'm sizing a duct just for the ventilation air. And what's the point here? Okay, I may want to try to get all of my zones into this category because I maybe don't want to be trying to run. I want to have an exposed ceiling in my beautiful, pool or whatever it is you're designing, and I don't want to have ducts exposed there or behind a plenum. This information helps us understand what kind of system we would want to meet our architectural goals. So that's another reason why we're doing it. Okay, is there anything else? One other thing I would say is that these totals down here are perhaps not useful in this case because now, like if what I would probably do here is that I would say, okay, this is a VAV system with a boiler. Oh no, it's an air source heat pump, but it could be the same air source heat pump for both. So maybe I'll add these two together and look for a piece of equipment that delivers that. Or maybe I make this one not an air source heat pump. Maybe this is a condensing boiler, and I just want to have one place with this condensing boiler. and chiller or something like that for cooling. So then I would look at these individual outputs for each zone and size the equipment. Okay, so I think that is a real whirlwind, quick introduction. That's enough, and I hope it's helpful. And as with always, just ask me questions, send me your models. This is an attempt to just get us started.